you lovely lot, I'm Teacher Jess and welcome back to Geo Cafe. Have you ever noticed how the clouds seem to change throughout the course of the day? So you might wake up in the morning and it's completely foggy or cloudy, and then throughout the course of the day it clears up. Or how it's the other way around. You might be having a sunny, lovely day, and then by the afternoon you got this complete cloud cover, or maybe even rain. So that's what we're going to be taking a look at. How the humidity and the temperature influences the cloud cover and formation throughout the day. Let's check it out. Humidity basically just tells us how much water is in the atmosphere, and how much water the atmosphere can hold depends on the temperature of the air. So we have different ways of measuring humidity. We have specific humidity, which looks at the weight of the water compared to the weight of the dry air. We also have absolute humidity, which looks at the weight, or the mass, I should say, the mass of the water compared to the volume of the dry air. But the one that we use most frequently is relative humidity. Relative humidity tells us how much water vapor there is compared to how much water vapor there can be. It is given as a percentage, and it shows you basically how full the air is. So if the air is at 100% humidity, it means that it's holding as much water vapor as it possibly can. If the air has a lower percentage humidity, it means that it can hold more water vapor. And the reason why this is a relative, a percentage, a fraction, is because how much the air can hold does depend on the temperature. So I want to do a few little diagrams that helps explain this, and we'll see if it makes sense in then understanding what condensation level is and what dew point is. So there are two major factors that will affect our relative humidity. The one is the temperature, and the one is the water that is in the air. If you have a higher temperature, it can hold more water, so it has more space for water. If we have a lower temperature, it can hold less water. If we have more water in the space, it will have a higher humidity. If we have less water in the space, it will have a lower humidity. Okay, I'm going to get Canva up, and then we are going to see if we can understand this using a few diagrams. So I want us to remember that when things cool, they will get smaller. As things heat, they will expand and they'll get bigger. So I'm first going to start by just drawing a container. I'm going to say that this is basically like a glass of water. Okay, so there's a glass. The inside space tells us how much this glass can hold. So when it is cold, the space will contract. So our glass, our container over here would get smaller. So far, that making sense. Obviously, it's not like that dramatic, but we're getting the picture. So if something is warmer, it will expand and then we'll have more space inside. So in the same way, warm air has more space to hold water vapor, and cold air has less space. So now we're going to actually fill this a little bit. I want to make this a little bit bigger. There we go. So there we can see, if we filled up this glass like this, I would say that's about 2/3 full. Let's say 60%. 60, there's still space for more. If we take that same amount of water, more or less, and fill it up in here, there. So more or less the same amount in the cold glass, we can see that it looks more full. So let's estimate this, let's say this is 80%. Okay, that is about 80% full. So I can see that the same amount of water has different percentage depending on how much the glass can actually hold. I'm going to go into this one a little bit more depth, but I do also want to point out how water can influence the humidity percentage as well. Let's just assume that these are all the same temperature. Okay, if I fill the glass up to here, we can maybe call this a third. Let's say about 30%. If I fill the glass up to here, philosophical question, is it half empty or half full? Either way, it's 50%. And let's fill one to about here. There we go. Let's call that about 80% full. So for all three of these, we have the same size container, but the amount of water that was in the container changed. That's why the percentage changed. So the more water vapor you have in the atmosphere, the higher the humidity, the higher the percentage and the relative humidity. So that was the first point, was the second. Sorry, that was the second point there. Water that's present in the air. Now I want to show you how temperature affects this. So here is my water in my first container. And I was saying that as the temperature changes, the relative humidity will change as well. So let's say that this is the glass, the container. At what temperature should we use? 30 degrees. And then, so we're going to have another one that's maybe going to be like 25. For all four of these temperatures, I'm going to work with the assumption that we have the same amount of water. So same amount of water for all of the containers. But because it's getting cooler, the container is contracting. It's getting smaller, so it can hold less. It can't hold as much. And again, it's a little bit colder, so it's contracted some more. And then one more time, 15 degrees. Let's put in some percentages for each of these. Let's say 60? 60, sure. So that's about 60% full, so 60% humidity. This one, this looks more, it looks a bit more like a 3/4 kind of thing. So let's say 75. There we go. This one is almost full, should we say like 90%? And then this one is full. It can't hold any more water. So that is 100%. Okay, so the last one, the 15 degrees, is 100%. It is full. It is done. This one we would then say is saturated. It can't hold any more water. You try to give it more water and it's going to throw it right back at you. And that's the basis of rain, or condensation, I should say. So if we keep trying to give this more water, it's going to push that water back out again. So this is saturated. So our last container, the last glass, is completely full. It's saturated. So 100% humidity means that the air cannot hold any more water vapor. But we assumed that it had this amount of water in it every time. I'm going to change the amount of water and we're going to see what happens. This time we are starting with less water over there. So the container is shrinking because it's getting colder. The relative humidity is increasing. But notice what happens when it gets to the 15 degrees. It's not at 100%. It's not saturated yet because it started with less water. It has less water vapor in it, so it hasn't become saturated yet. It needs to keep getting colder before we actually reach that 100%. So let's keep going. Okay, let me duplicate that again. Fantastic. I think we can see that nicely now. So again, in all of these containers, we had the same amount of water, but because it keeps getting colder, the container keeps shrinking and the amount of water vapor that the air can hold becomes less and less. So now we have our humidity for these different containers. So we have the percentage of how full it is. And you can see that even though that one, that 15 degrees, and that 15 degrees have the same size container, they have different humidities. So even though it's the same temperature, it's a different humidity. And the reason why is because that one had more water vapor than this one. So this one, for it to reach that 100%, for it to reach that full saturated capacity, it had to get as cold as 5 degrees Celsius. These temperatures, these temperatures where the air reaches saturation, where it reaches 100% humidity, it always changes and it has a name. So that temperature we call dew point temperature. That's this, dew point temperature. So dew point temperature is where the air is completely saturated, it's 100% humidity, and it will start to condense. That value, that temperature, will depend on how much water vapor was in the air to start with. In the atmosphere, we can't necessarily just make the air colder, but the air does become colder as it increases in altitude. So as the air rises up from the ground, it becomes colder. And we call that a lapse rate, a dry adiabatic lapse rate. And the rule is that it will get colder by 1 degree Celsius for every 100 meters. So until it finally condenses into a cloud, this is how much colder the air will get as it moves up in the atmosphere. Let's draw ourselves a little diagram. So this is the ground, and as we move up, we are moving up in the atmosphere. So we can see that it's warm by the ground, and as it goes up into the atmosphere, the air gets colder and colder. As the air gets colder and colder, again, it can hold less and less water vapor. So we are going to reimagine our glasses as little parcels of air. And I said that it gets cooler by 1 degree Celsius for every 100 meters that it goes up. So we can see that I've been getting cooler by 5 degrees at a time. So then our intervals need to go up by 500 meters. Great, so I have my parcel of air over here. So as it goes up, the parcel of air is contracting because it's getting cooler and it can hold less water vapor. Now let's assume that it started with a certain amount of water. You are welcome to suggest a better platform for using as a whiteboard. So far, this is the best one that I can find that actually kind of works for my diagrams and explanations. But if you know of something that might work better, please do share. Okay, so as the parcel rises, then the air can hold less and less water vapor because it's getting cooler and cooler. So we can see that it has to rise up before it's reached a high enough humidity for it to actually condense and become saturated. If we look at the temperature over here, it was 20 degrees before it finally reached 100%. For this particular parcel, dew point was 20 degrees Celsius. Another question was, where did this dew point happen? And that is where this altitude comes in. So how high up did the parcel of air have to go before it was cold enough to condense? And that is 1,000 meters. If we have the same thing happening with less water in the atmosphere, let's say about there, and then as it rises up, the air can hold less and less water vapor until it is at 100%, it is full, it can't hold any more, and then it is saturated. Here, the temperature was 10 degrees Celsius and the altitude was 2,000 meters. So it had to rise up 2,000 meters before it reached the temperature where it was saturated. That height that it needs to rise is condensation level. So condensation level is the altitude or the height above sea level where you will have condensation or where the atmosphere, the air will reach dew point temperature. So dew point is the temperature where the water vapor will condense, where the air is saturated, and then condensation level is how high above sea level the air needs to be before it's reached this dew point temperature. So naturally, the more water vapor that is in the air already, the less it needs to cool, the less it needs to rise and cool before it reaches this 100%. But if it's quite dry, it needs to rise a lot before it reaches dew point temperature. So over here, we would see a cloud forming on this layer, and then over here, we would see a cloud forming on that layer. Obviously, all of these will also change if this temperature is different. So if the temperature at the base was maybe something lower, then maybe condensation will happen lower, or dew point temperature would be closer to the ground, or condensation level will be closer to the ground. And that's why you get these clouds and the condensation at different heights in the atmosphere. Now comes a question that a lot of people wonder. Why do we notice humidity or different types of clouds throughout the course of the day? So maybe in the mornings, you'll see that there's more cloud cover, and then throughout the course of the day, it starts to clear up. Or maybe you have, they're predicting rain or thunderstorms that doesn't come for like the whole day until maybe the afternoon or the evening. And all of that is related to the temperature. The temperature will then influence the humidity. So let's take a hypothetical question over here. Let's say that the temperature is rising throughout the course of the day, and as it gets warmer, it is evaporating more water vapor. So if we go back to our diagram, so let's say at the start of the day, it is cold, there isn't much water vapor in the air. It's probably quite humid because it is so cold, so it doesn't hold a lot of water vapor, so it will have quite a high humidity. Maybe you'll see like a little bit of fog, or maybe you'll see some clouds or something like that. As it starts to warm up, the air can hold more water vapor. Okay, so the air is warmer, it can hold more water vapor, and the relative humidity is lower. Because it's warmer, it might also be evaporating more water, and we will find more water vapor in the atmosphere. Then as we get to the afternoon, where it starts to cool, now the temperature will drop, and you'll see that the water vapor that it can hold will decrease. So our parcel gets a little bit smaller, and now it is saturated. So early morning, less water vapor, it warms up, it evaporates some more water, it gains some more water vapor, and as it cools into the afternoon, it can hold less vapor, and now suddenly it is full from all of that water vapor it had evaporated, and it reaches saturation point. Okay, so by the afternoon, where it is the warmest, it has the most water in it, and as it begins to cool, it can't hold as much anymore, and the humidity will increase, so we have rain clouds or clouds that could form. This is one of the ways that a lot of thunderstorms occur in very warm areas. Then I just want to briefly take a look at the different types of clouds that we can get from this. You could see that the condensation would happen at different points in the atmosphere, and that does result in different types of clouds. Now, there are loads of different clouds, and I'm not going to go through all of their names. I'm just going to go through 5 very important words that will help you learn all of the names that you would need to know for the different types of clouds. The first important word that you need to know is cirrus. Cirrus means curly or wispy. And when you think of cirrus clouds, you think of these little strands of curls, these fluffy clouds, or these little thin clouds that look like puffs of smoke. And you usually see these really high up in the atmosphere, and they're very often made up of ice crystals. The second word you need to know is alto. Alto means high, or we can think higher. It just means that it is higher than normal other types of clouds. It's not as high as cirrus clouds, it's just higher than regular clouds. Then we have stratus. Stratus means layer. So where you have a layer of clouds, you have stratus clouds. And then we get to cumulus. These are probably the most frequent or common type of cloud. So we see these scattered on a typical beautiful day with these lovely little fluffy clouds everywhere. And what I like about this picture that I also want to point out is, do you see the flat bottom on all of these clouds? There's a reason for that flat bottom on the cumulus cloud. That reason is the condensation level. That flat part under the cloud, you can see all of them have it. That is how high the air had to rise, or the water vapor had to rise for it to reach dew point temperature. So that's how high the air had to rise up before it would finally condense. So that's why you see that flat base, because anything below that is too warm, so the humidity would be too low, and then above that it's cool enough for it to condense. And then finally, the last one is nimbus, and that is rain. Now, the reason why you only need to know these 5 words is that all of these words combined name most of our common clouds. So if we take a look towards the ground, so the lower layer clouds, we have mostly cumulus and stratus. So cumulus means a clump or a little heap of fluffy clouds, and that is usually scattered around in a lovely sunny day. But if it's more of like a layer of fluffy clouds, then it would be a stratocumulus. If we have a layer of clouds that's bringing rain, it would be a nimbostratus. Nimbo being rain, stratus being layer. So a layer of rain clouds. If we go higher, we can see the alto. They are the alto clouds. So if we have higher fluffy clumpy clouds, they are alto cumulus. Or if we have a higher layer of clouds, it's altostratus. And then finally we get to the cirrus clouds. These are all the way up at the top. We get the classic just cirrus, which are your lovely curly clouds over there. You can get your cirrocumulus, which kind of is like these tiny little speckles, of like this layer of little speckles. And then you can also get the cirrostratus, which is actually quite difficult to see by itself, but you can make it out when you have this general haze and halo over the sun. You can also sometimes see it at night when you have this halo around the moon as well. And then finally, my personal favorite cloud, the cumulonimbus cloud. The cumulonimbus is formed by cumulus clouds that just keep growing and growing and growing, and it just gets taller and taller and taller until it's worked its way through all 3 layers. So it's one of the very few clouds that actually go from the low layer through to the high layer clouds, and it brings heavy amounts of rain or thunderstorms. So these are your thunderstorm or your storm clouds. I have no idea what questions are in these quizzes, but I thought maybe we can see if we can identify a few clouds based on the pictures. Let's give it a try. Okay, so something forms when water vapor cools and condenses around particles of dust and smoke to make tiny water droplets that gather together. Well, I'm going to assume it's the theme of this quiz, which is clouds. Yes, so clouds will form when water vapor condenses. They mention that it's around these tiny little particles of dust and smoke. We call those condensation nuclei. I think I lost my time bonus. Oops. Okay, blank clouds form in layers. So a layer cloud is stratus. Yay. Blank clouds look like cotton balls. They're puffy and white with flat bottoms. Hopefully you remember, those are cumulus. Nice. Something clouds are middle clouds. They look like cotton balls. I'm actually kind of stuck because I would think middle clouds would be alto. But I don't really see an option like that. Fluffy cotton balls, I would assume cumulus. I know that cumulus stratus. Oh, stratus can also have those little fluffy type of clouds. I'm gonna go cumulus. Yes. Oh, okay. Whew. Something clouds are low clouds that look like bed sheets covering the sky. Okay, a blanket or a layer would be stratus. Wonderful. Something clouds are wispy and feather-like clouds. I like that description, feather-like. Yes, it does kind of look a bit like feathers. Okay, and those are cirrus clouds. Wonderful. Clouds are made of dust, smoke, and, well, we don't have water in this mix, so we need some water droplets. We need something to condense. Here we go. Something causes water droplets to fall to earth. This is called rain. Well, gravity. Gravity is the thing that makes stuff fall to the ground. Something clouds are high clouds that look like feathers. We've had this one already. Cirrus. And fog is made of low something clouds. I guess stratus? I think because it's like a layer. I I would say stratus. Oh, good. I actually wasn't sure there. Well, that was fantastic. We know our clouds. Okay, well, thank you very much for joining. I hope that you learned something new or maybe had a few questions answered. And I hope to see you again next time. And have a lovely day further. Cheers. Bye.